Onu seneye öğreneceksiniz zaten. Okay, so any questions before we begin? We will be discussing the last capacitor problem where you probably found out that energy is not conserved. Now, any questions before that? Now, if you remember the question, you were told that you initially charge a capacitor which has capacitance C1 to a charge, let's say initially it has a charge plus Q and minus Q. Then after you charge it, you connect it to a second battery. So this is the C2. There's a switch. Before the switch is turned off, is closed, there is nothing, so the first capacitor is charged. When you close the switch, some charges will be distributed between these two capacitors. So let's say this will have a charge Q1 plus Q1 minus Q1. The other one will have a charge plus Q2 and minus Q2. And then you were first required to find what the charges are. Well, to find the charges, we will be using the conservation of the charge, which tells me that Q should be equal to Q1 plus Q2. You see, this is the Q1 plus Q2 is the total charge in this conductor over here, this whole conductor. And before, the total charge in the same conductor was total Q. Since charge should be conserved, total large Q has to be equal to Q1 plus Q2. This is charge conservation. Now, secondly, since here everything in statics now, we are talking about electrostatics in this case, we know that the potential difference across these 2 points should be equal to the potential difference across these 2 points. So which tells you that Q1 over C1 should be equal to Q2 over C2. So this is your second condition to determine Q1 and Q2. So you have 2 equations to determine these charges. Then the problem of energy. The first one, initially, there is no energy stored in this capacitor, only there's some energy stored in this first capacitor, and the total energy stored in that capacitor you can write as Q squared over 2C1. Now in the final case, there is some energy stored in the first capacitor. There's also some energy stored in the second capacitor. So if you calculate the total energy stored in the capacitors, that is Q1 squared divided by 2C1 plus Q2 squared divided by 2C2. This is the total energy stored in both of the capacitors, and you should find that these are not equal. Now the question is up to this point. Now what? Now, you see, I quite often criticize you for being too much based on questions. Questions at the end of the chapters, questions in the exam, questions in the homework, or the solutions of the questions. You go around trying to find solutions to the questions. And when you find these questions, solutions, this is where you stop. So there's a problem. There are methods of solving that problem. You apply those steps, and you obtain a solution, and you're done. But actual research starts after this point. Now, you found that energy is violated. Why? So that is when the real thing starts. So you have a few alternatives at this point. You can say that, okay, maybe energy conservation is not a law. I mean, there are certain circumstances in which energy can be violated. And maybe this is one of them. And then, of course, the question is, this is a hypothesis which should be checked, whether you should prove it or disprove it. And we have all the kinds of proofs in which energy should be conserved. And then if you say that energy is not necessarily conserved in every case, then you should find some flaws in our previous proofs. So why those derivations do not apply in this case? That is the next thing you should study, you should research. Well, energy conservation, at least the question and the answer to this apparent, I say, paradox is that this is not, energy is conserved. That's not the reason why we find energy violation in this problem. The second possibility is that maybe you did a mistake in your computation. There were some steps in which you missed. You missed some factors, etc. Well, there are many of you here, and if you had asked your friends, there are a significant number of you who found the same result independent of each other. So that's where the group, working in group part enters into the game of doing science. Science you have to do in groups, you have to discuss with other people. There are other people who have done the same computation independent of you without checking your computation or checking your idea, and they obtain the same result. So it's likely that you didn't make a mistake in your computation. So energy should be conserved if you accept that hypothesis, and you didn't make any computational mistake, then how can we understand this one? This is just a simple system. So in that case, there should be something else. You see, this is our initial energy stored. This is the initial energy. So we have a system. Initially, we look at our system, and we see that it has some potential energy, no kinetic energy, nothing else. That's just the potential energy. And then something happens to the system, the charges are redistributed, etc. And then we get this configuration, where we can again calculate the energy, the potential energy stored in the capacitors. And this is our result. So in between, there should be something that we ignored that can explain this difference. Well, your friend says heat. Where does the heat come from? We are studying electricity.
Electrons.
So there's a resistance. So now your friend has a hypothesis. Your friend claims that the difference in the energy is caused due to the resistance. Well, that was an assumption we made in using the energy conservation. We assumed that there is no resistance in the circuit. In that case, the initial potential energy should be equal to the final potential energy. So if we put some resistance somewhere, it will dissipate some of our energy, so it will create some difference between the initial potential energy stored in my system and the final potential energy stored in my system. So that is a hypothesis which needs proof. The weird thing, though, is that you see the difference in the potential energy stored is independent of resistance. We know the power of the resistance depends on the resistor. So if you have a different resistor with a different resistance carrying the same current, its power will be different. But here the energy difference, the total energy dissipated by the resistor should be independent. That is, we have a hypothesis. It should explain this energy difference independent of which value of the resistance we use. Well, there is also another question that should be answered. If it is independent of the resistance, why can't we set it to 0? If we set it to 0, then there shouldn't be any power dissipated by the resistor, and so it won't be an answer. So it is still to be answered. You have a hypothesis now, which you need to prove. The resistance hypothesis. And, well, that will be in your next homework. So you will just put a resistor over there and try to calculate the power dissipated by that resistor. Now, any questions before we continue? But if you calculate them, solving these two equations, you can solve for Q1 and Q2 in terms of large Q and the capacitances, and it turns out that these two are not equal. That is the solution. Just solve these equations, put it over here, you will see that there is a difference. Any other questions on resistors, resistances, capacitance? If you want to bring your homework This is your final chance. Yes. Well, that will be your next homework. I mean, your friend has a hypothesis, says that it is the resistance of the wires that we ignored. That is a hypothesis. Of course, I have some doubts. I claim that, well, if it is the resistance that is causing this difference, then the difference should depend on the resistance of the resistor, whereas here it doesn't seem to depend. So if it doesn't depend, I can easily set the resistance to 0, and this should also work in that case. But of course, you have to work out the details. You should calculate how much power, how much energy is dissipated by the resistance to prove me wrong or to prove him right. So you will figure it out. Of course, to figure it out, you first have to learn how to study the circuits. So let's start with the circuits. Now, we will be discussing a weird concept. I mean, that we will use this symbol to denote this weird E. It's called the epsilon. Now, this is called electromotive force. But just keep in mind, this EMF or EMF is not a force. Although its name contains a force, it is not a force. Don't get confused. So what it is? Well, we were considering batteries. Also on Tuesday, yesterday, last week, we started considering batteries. We said that, okay, if you have a battery, if you connect it to a resistor, it will take electrons from one side and give electrons to the other side. So this is what the battery does. Well, you see, this is a high potential, so this is a low potential energy region for the electron. This is the high potential energy region for the electron, and we said that the battery just gives some potential energy to the electron. It moves the electron from a lower potential to lower potential energy to a higher potential energy. Or if we imagine in terms of this imaginary positive charges, it moves positive charges from low potential to high potential. So basically giving them energy, whatever you consider, whether you consider the positive charges as your current or the negative charges as your current, what a battery does is that it takes charge carriers at a low potential energy and give them some energy so that they will be moved to a region where they have a larger potential energy. Now, this energy that the battery gives to the charges is what we call the electromotive force. Well, it doesn't have to be just the battery. We will see that the electromotive force is a general definition that we will be using also in other circumstances. It's kind of the energy that you give to the charges, to a unit charge, let's say. That is what we call the electromotive force. It is quite similar to the voltage. Very similar. I mean, that is one of the main reasons why it is so confusing. Why do we need a different concept? The voltage of a battery is what we said, that the charges, as a unit charge moves from the unit positive charge moves from the negative terminal to the positive terminal, the energy gained by that charge is what we call the voltage of the battery. But that's not actually the voltage. The proper term will be the EMF. Now, the difference is especially seen when you consider, for example, a real battery. Now, what we mean by a real battery is, well, we were always talking about the batteries. They are this is the ideal battery. which we can say that it's a source of EMF. And if we attach a resistance to it, it has some internal resistance. This whole thing is a real battery. It has a resistance, an internal resistance. Now, we will see the effect of this internal resistance, and we will see that the potential difference that you measure across a real battery will be, in fact, a function of the current running through it. So if there is a current running through it in this direction, we will see that this is A, this is B. The potential difference across AB is not equal to the EMF of the battery. The EMF is a constant. It doesn't depend on the EMF of the battery is a constant. It doesn't depend on the current. But the voltage across a battery does depend on the current. That is kind of the main difference, in the case of the battery at least, the main difference between the EMF and the voltage of a battery. Let's do a few examples. Let's first look at an ideal battery, where the EMF and the voltage doesn't really have any difference. Now, how can we determine the current? Well, one way to do is you can just say, okay, the potential difference across this resistor is just I times R between these points A and B. This is equal to I times R. But the battery just provides a constant potential difference V across its terminals. So the potential difference across A and B should be equal to V. Or let's use the other symbol, EMF. Let's get used to it. And this tells me that the current is epsilon over R. This is the relation between the current and the EMF. Now, to see the difference in the potential, now let's replace this with a realistic battery. A realistic battery would be, okay, an EMF source plus an internal resistance, plus we have this external resistor. This is large R, this is small r. Now, we already know that the equivalent resistance, we had already studied, is the sum of these two resistances. So the current running through our system is, in fact, epsilon over R plus R. Now, let's look at the potential. Well, another way of obtaining, in fact, the same result will be just to look at the potential difference between A and B, which is, okay, it is I times R. But it will be also epsilon minus I times R. Because this point is at a larger potential than this point due to the battery. But then we have a potential drop across the resistor, which is I times small r. So this is the VAB is the potential across the battery. So this is our real battery. So this is less than epsilon, less than or equal to epsilon. The voltage across a battery will be smaller than the EMF of the battery. And the difference will be determined by the current and the internal resistance. So if you buy a 1.5 volt battery, if you put it in a circuit and measure the potential across your battery, you will not be able to measure 1.5 volts. You will be measuring something smaller. If you remove the battery from the circuit and connect it to a voltmeter, which allows you to measure the potential differences, it will read 1.5 volts. But when you connect it to a circuit, it will read less than 1.15 volts. So if for some reason your circuit needs at least 1 volt to work, you should better get a battery that creates more than 1 volt. Because due to the current running through your circuit, the potential difference across the terminals created by the battery will be less than its EMF. And the unit of EMF is also voltage. It's just like the potential difference. Now, any questions? For most applications, whenever you see an EMF, you can think of the voltage or potential difference. For most applications, not all of them. We will, in the future, in the following several weeks, after a few weeks, we will be studying systems in which you cannot talk about voltage. But nevertheless, you can still talk about the EMF. So in that, when we reach there, the distinction between EMF and voltage will be more clear. No, what I said was the potential difference and the EMF, they are different concepts. At this point, they look very similar, and in fact, they are actually very similar concepts. One important difference when you are talking about the battery is that the EMF and the voltage that you measure across a battery, they might be different. As concepts, they are different concepts. Their values can be equal. If you take a battery that is not connected to a circuit, the voltage across the terminals will be equal to the EMF of the battery. But in a circuit, they will, numerically also, they will be different. Conceptually, they are different concepts. Now, of course, we will be trying to analyze some complicated circuits, not just this simple circuits like this one where we have a battery, a single battery connected in series with a couple of resistors, or a single battery connected to a couple of resistors in parallel. We will have much more complicated circuits. And so the question is, how can we study these circuits? For example, one circuit that we can consider is this one. Now, even this one is somewhat complicated. Epsilon 1, epsilon 2. Which way does the current flow? So how do we study these circuits? So here you see there are not just one, but two batteries. And both of the batteries are trying to run the circuit in the opposite directions. If there was no the second battery, the current would be running in the clockwise sense. And if this is absent, then it will be running in the counterclockwise sense. Now we have both of them, now what?
Can we just sum them?
That is what we will do, but how do we know? That, as I said, that is a hypothesis. Just sum them up. Or take the difference. Can we prove it? Using the basic concepts that we have been studying. Now, there will be basically two rules that we will be following. Now, let's go back to this simple circuit. Now, basically, we will be analyzing the principles that we want to develop should be applicable to the more complicated circuits as well as to the much simpler circuits like this. So just studying this simple circuits, we can get a feeling of how these principles will work. And after that, we can apply them to more complicated cases. Let's say we have an EMF source. Now, before we talked about the potential changes, the differences in the potentials to obtain this result. But now we can also use, let's say, energy conservation. Of course, assuming energy will be conserved in such a simple circuit. Now, energy conservation tells me that, let's say, there is a current running through it, and after time dt, what is the total work done by the battery? Within a time dt, the work done by the battery this work is done either by, converting chemical energy into electrical energy, or by using the solar energy to create some electrical energy, or whatever you can imagine. So After time dt, what is the total work done by the battery? I times, let me write it in this form. Now you see, we define the EMF as the energy given to the circuit, or energy given to the charge, per unit charge. That is the EMF, per charge. In a time dt, this much charge passes through my battery, because we define the current as the charge that passes per unit time. So if you multiply I with dt, you obtain the total charge passing through my circuit. So this much charge passes through my circuit, or through my battery, and each one of those unit charges receive this much energy. So this is the total energy received by my charges from the battery. And how much energy is dissipated by the resistor? The resistor also dissipates energy, so there will be some energy loss. What is the power dissipated by the resistor? Well, in fact, you can just use the same principle. The potential difference across the resistor is just I times R. This is how much energy each unit charge, each positive unit charge dissipates as it goes from one side of the resistor to the other side. So the total number of charges that passes through the resistor is given by I times dt. So we can just cancel I dt from both sides. So we obtain epsilon is equal to I times R. The result that you already know. So this is one thing that we can use. The energy conservation. How much energy do we give to the system? How much energy is dissipated by the system? Well, it works. It will work all the time. But the problem is energy conservation is just a single equation. So that is something that is not so nice. Now let's look at the change in the potentials. Let's consider this point A. Okay, let me also give names to other points, A, B, C, and D. VAA, the potential difference between the point A and the point A, it should be 0. But I can also say this as VAB plus VBC plus VCD plus VDA. The potential difference between the point A and A is the potential at the point A minus the potential at the point B, plus the potential at the point B minus the potential at the point C, plus the potential at the point C minus the potential at the point D, etc. So VAA, we know that it is 0, but at the same time we should be able to write it in this form. So let's write each one of these terms. Let me just write the change as the drops in the potential. Now, what is the potential difference between A and B? The potential drop as you go from A to B? 0, there is no resistance. Between B and C? I times R, so we are crossing, there's a current I running across this resistor, and we are crossing that resistor, so it is I times R. This is the potential drop. Between the point C and D, there is no resistance. Between the point D and A, epsilon or minus epsilon. Remember, I'm writing down the potential drops. So the positive terminal of the battery is at a higher potential. So the potential increases from D to A. So there is a potential increase by epsilon. But I can also say the same thing as there is a potential drop of minus epsilon. So I have adding epsilon is the same thing as subtracting minus epsilon. So the potential drop is minus epsilon. So this should be 0, and again we obtain the same result. Epsilon is equal to I times R. Is it clear why I put this minus sign over here? Now, up to this point, we have always ignored the signs. We ignore the sign of the capacitance, we ignore the sign of the resistances, etc. From this point on, we will be trying to kind of insert the signs. This is one place where we inserted a sign based on which direction we moved. Now let's go back to our previous example. Or this is epsilon 1, this is epsilon 2. Now there's one problem now. I don't know which direction the current flows. Well, I don't really care. Now what I will be doing is that I will define the positive direction of the current. So I will say that a current is positive if it is running, let's say, in this direction. If the current is running clockwise, I will say that the current is positive. It might turn out that the current is negative, which will tell me that the current is running in the counterclockwise direction. So this sign over here, at least in this case, will not mean that the current is running in that direction. I don't know that. But it will just mean that the current will be positive if it is running in that direction. So this is the negative, this is the positive terminal, negative, the positive terminal. A, B, C, D. Let's write the potential drop from the point A to the point A. It should be 0. As I go from A to B, what is the potential drop?
0.
It is 0. There's no resistance over there. So there's no potential difference between those 2 points, A and B. Now, what is the potential drop as I go from B to C? Now, this time B is at a higher potential, C is at a lower potential. The difference is epsilon 2, so the potential drop from B to C is epsilon 2. From C to D, what is the potential drop? Well, there is one question though. I don't know the direction of the current. So should I put a plus sign or a minus sign? Plus sign. Why?
Because I is not defined.
Well, we can find this version of I to be positive, so we will define this to be positive. It turns out to be, it turns out that I is in this direction negative.
Well, kind of. You see, whether this I is positive or negative, this expression will always be true. Let's say if I is positive, in that case we know that C is at a higher potential than D, so the potential drop will be a positive number, which will be I times R. If I is negative, it means C is at a lower potential than D, so as we go from C to D, the potential increases, it doesn't drop. So we can write an increase in the potential as a negative potential drop, so the potential drop should be negative. But if I is negative, I times R is already negative. So I don't need to add any other additional signs over here. So it's a plus I times R. Whether I is positive or negative, this sign will be always true. It's independent of the sign of I. And then finally we went from C to D, from D to A. What is the potential drop? The potential from D to A is increasing. A is at a higher potential than D. So a potential increase by epsilon 1 is a potential drop by minus epsilon 1. So this sign is correct. And so we can just solve for the current. I is equal to epsilon 1 minus epsilon 2 over R. So we see that if the first battery has a larger EMF, then it will decide on the direction of the current, whereas if the other battery has a larger EMF, then it will decide the direction of the current. And we can also reproduce our previous results. Let's say that if epsilon 2 is 0, there is no battery over here. Then there is a single battery and a single resistor, so the current should be epsilon 1 over R, and it is indeed epsilon 1 over R. If we are missing this first battery, we don't put a battery over there, so epsilon 1, we can just set it to 0. In that case, I just becomes minus epsilon 2 over R. Well, the additional minus sign is just telling me that the current is running in this direction, in the counterclockwise sense, and its value is epsilon 2 over R. This one. Well, you see, we are going from A to A. So we started from A, then we went to B. There's no potential drop. And from B to C, well, you see, the battery, the positive terminal of the battery has a larger potential than the negative terminal. In the EMF, that is in the absence of the internal resistance, EMF is the potential difference between the terminals of the battery. So as we go from B to C, we are going from a high potential to a low potential. So the potential drops by epsilon 2. So that is why here we are, I have decided to write the potential drops. So the potential drops across this battery is epsilon 2. So that's why it's positive epsilon 2. You could have chosen to write the potential increases. It will be the same. So you can start from A, go around A, sum all the potential increases, and you will still get the same equation. The only thing that will be different will be all these terms will have the opposite signs. But the left-hand side will still be 0, because the point A, the potential difference between point A and point A is 0. Other questions? We can just choose the opposite direction as our positive direction. It should also give me the same answer. Let's also try that. So this is my system. Epsilon 1, epsilon 2, CD. So let's say this. Let's take the opposite direction as our positive sense of the current. And again, let's go from A, B, C, D, etc. 0 should be equal to VAB plus VBC plus VCD plus VDA. What is the potential drop as we go from A to B? From A to P, what is the potential drop? 0. There is no resistance. The potential difference across a battery is just 0 current times the resistance. If there is no resistance, there is no potential difference. Okay, from B to C, what is the potential drop? So is it plus or minus epsilon 2? Potential drop as we go from point B to C is plus epsilon 2. Again, I'm going from the positive terminal of the battery to the negative terminal of the battery. So the B is at a larger potential than C, and the difference is epsilon 2, so the potential drop is epsilon 2, so it's positive. So what is the potential drop across C and D? Okay, we know that it is the potential difference is I times R. So this is the potential difference across the battery. Now the problem is with the sign. Which sign should we use? Let's see. Let's look at the case when I is positive. If the current is positive, that means the current is running in this direction. But if the current is running in this direction, it tells me that C is at a lower potential than D. Since the current is across a resistor, the current will always go from the high potential to the low potential. It is losing an energy and it's dissipating it. So If I is positive, then D is at a larger potential than C. So from C to D, the potential is increasing. Since the potential is increasing from C to D, the potential drop should be negative if I is positive. So I is positive, I times R is positive. The potential drop as we go from C to D should be negative, so we have this minus sign. If I is positive. Now, if I is negative, that means the current is running in this direction. Across the resistor, the current goes from the high potential to the low potential. And so since the current is going from C to D, so the potential drops across the resistor. And the magnitude of the drop should be I times R. But remember, I is negative. So I should put a positive number over here. Minus I times R is a positive number if I is negative. So that's why whether I is positive or negative, we should always have this minus sign over there. You see, the thing that will be confusing you the most will be the signs. So I'm sure you have memorized all from the high school that the potential drop across the battery is I times R, the current times the resistance. Now we will be adding capacitors to our circuits, and you know that the potential difference across the capacitor is just Q over the capacitance. So these are all memorized. I'm sure you can just write it down. The problem is how you determine these signs. So if you are getting confused, ask. The reason why we have this minus sign over here when the current is running in this direction is that the current across a capacitor, the current always runs from the positive, a larger potential to the to smaller potential. So if I is positive, D is at a larger potential. So the potential drop as we go from C to D should be negative if I is positive. That is why we have to include this minus sign over there. And then let's continue from D to A, the potential drop is, well, A is at a larger potential by epsilon 1. So the potential drop from D to A is minus epsilon 1. And we find that I is equal to epsilon 2 minus epsilon 1 over R. In the previous case, we find I to be epsilon 1 minus epsilon 2, and now we find I to be epsilon 2 minus epsilon 1. There's a sign difference. Which one is correct? Both of them are correct. I mean, they just look different because they refer to different directions for the positive direction. If a current is running in this direction, with this convention, it is a positive current. With this convention, it should be a negative current. So that is why we have this sign difference between these two results. Both of them are correct. That's also another reason why you should be careful about defining your conventions beforehand. So if you just use different conventions, you will get different results, and both of them will be correct. You have to define your conventions. Which direction is the positive sense? Which direction is the negative sense? Now, any questions up to this point?
Epsilon 2 is smaller than epsilon 1. The way we choose the current is flowing is wrong.
It's not wrong. I'm defining the positive direction of the current. The current can be negative. If epsilon 2 is smaller than epsilon 1, it just means that since this is negative, it's telling me this is the positive direction, so it should be running in the negative direction. No, nothing changes. I mean, you see, this circuit or this circuit, they are the same circuit. Nothing changes if you change your direction of the positive sense. Nothing changes in the circuit. It's how you interpret your results that should be modified. It's just like if you remember in mechanics courses, in one dimension, we first chose the positive direction of the position. If you choose the positive direction to be over there, then my keyboard is at a distance, let's say 1 meter. If I choose the positive direction to be there, my keyboard is in the -1 meter. The only thing that changes is how I interpret this 1 meter or -1 meter. The position of my keyboard doesn't change. Here, whether you choose this direction or that direction for the current doesn't change the potential differences anywhere. The potential differences are determined by the current and these epsilons and the resistance, let's say. Whichever direction you choose, the potential between A and D is the same. Any questions? Okay, see you after 10 minutes.